Do you want to try sharing your screen or is it? Oh, all right. Wow, perfect. Do you want to try sharing your screen or?
Hi, Martin.
Hi, I think I was muted.
Yeah, it's okay. How are you?
Good, good. Thanks a lot for I don't know, remembering me and offering this
You're
opportunity.
welcome. Thank you accepting our invitation. It's very nice to see you again.
Same here.
Martin, since the time is coming, we don't want to keep you busy too much. So let me introduce very briefly, and then you can start if you want. So
Sounds great.
welcome everyone. Thank you very much. Thank you very much, Martin, for accepting our invitation again. And Martin Meyer from Romeo Observatory, Bamberg, will be talking about X-raying the stellar graveyard, mapping supernova remnants with eROSITA. Of course, eROSITA has been a great survey machine, but with its wide field of view compared to more regular Chandra and XMM, I believe it will contribute a lot significantly on the supernova remnants. And so hopefully we'll hear a very nice talk from Martin on how and what eros they actually observe. Thank you very much. Go ahead.
Yeah, thanks a lot for the nice introduction. Um, yes, I'm a postdoc at the Remes Observatory in Bamberg, and I'm not sure how familiar people are with Bamberg. There's a little cartoon down here which actually shows a historic sketch of our observatory. It's actually it's around 150 years old, and it's located in a sort of small town in northern Bavaria, close to Nuremberg, just in case people are not familiar with it. But at the observatory, we do lots of high energy astronomy. And the results I want to present to you today are mostly based on X-ray data based on this eROSITA All Sky survey. And I've decided to focus on what I've broadly called the stellar graveyard, which includes supernova remnants, but also, for example, neutron stars or pulsar wind nebulae. And I've decided to present you a few of my personal favorite results. and hope to convince you that there's quite a lot of interesting data out there. So just a brief outline what I'm going to talk about. I will start by introducing a little bit of what we learned from X-ray emission, particularly focusing on one hand supernova remnants, on the other hand neutron stars, or more specifically pulsars. And then I will introduce the eROSITA mission just briefly for us all to have an idea of what this all-sky survey actually did. And then I will reproduce some of the selected results regarding mostly galactic science with eROSITA, and I've tried to organize this into 3 broad pillars. The first one has to do with completely unexpected things that were found simply by eROSITA being an all-sky mission that looks in places people have not looked before. The second one being eROSITA's capability to map very, very large objects on the sky that are too large for other X-ray telescopes. And finally, the ability to actually study populations of certain types of objects and see how different objects change depending on their properties. But let's get started by simply introducing what I think of when I think of a supernova remnant. And I've put here this very, very simplistic sketch of how I think of a supernova remnant. We don't really need to understand how exactly a supernova is. All we need to know for this is that a supernova releases large amounts of energy and material, the so-called ejecta, into the environment. And since such a large amount of materials of energy is released, a shock wave forms. So basically a supersonic wave expanding into the surrounding interstellar medium. And since the shock wave can have speeds up to tens of thousands of kilometers per second, the surrounding interstellar medium gets heated to very, very high temperatures, maybe around 10 million Kelvin. So this surrounding interstellar medium will then start being a hot plasma, which we can see, for instance, in X-rays. And we call this shock wave the forward shock to discriminate from something that we call the reverse shock. This reverse shock you can basically think of as the information of the supernova ejecta being decelerated, traveling backwards. So this is basically a shock wave that travels backwards in the frame of the ejecta. And only after ejecta have been hit by this reverse shock do they become hot. Before this reverse shock has heated the material produced in the explosion, we actually cannot really see it in X-rays because it has become very cold on the timescale of a few years after the explosion of the supernova. Something I forgot to mention is that on this forward shock, we also have the possibility for very fast speeds that particles sort of surf on this shock wave, which means they get accelerated to relativistic energies up to maybe tera electron volt regimes, which is something that we can also observe, as you will see. Now, you may think that this picture on the right here is very simplistic, and I would agree with you. But I think if I overplot a real X-ray image of a supernova remnant, this is the famous object Cassiopeia A, you will quite nicely recognize these different shells that are shown in this sketch. You see on the outermost shell, this is sort of this rugged filamentary structure, which can be seen here in blue. And this is actually this forward shock wave. So there we see the explosion sort of traveling out into the interstellar medium. And then you have this even more chaotic and very colorful structure further on the inside, which is what I would call the reverse shock. So there you really see how the ejecta, the ashes of the explosion of the supernova, are being heated by this shockwave that travels backwards. And the reason we can see such supernova remnants in X-rays is because the hot plasma produces thermal Bremsstrahlung emissions, so sort of a continuum, which is superimposed with many, many bright emission lines. And the typical elements we see include, for instance, oxygen, silicon, iron, or also neon, magnesium, as you will see later. But there's a separate mechanism for these relativistic particles that I mentioned earlier that are accelerated here at the shock front, and that is synchrotron radiation. So basically, we have these relativistic particles spiraling around magnetic field lines, thereby losing energy, which produces a very, very hard characteristic spectrum. And the fact that it is hard can be seen also by the fact that it is mapped to this blue energy band, as we usually map the harder energies to the bluest bands. So here along the shock front, you really have relativistic electrons. And I think this already gives you a good idea of why we want to look at supernova remnants in X-rays. This includes, for instance, to study what is the material made of, what are the ejecta made of, how does the material actually get heated on small scales. This is actually a very complex process as this shock heating happens in a collisionless way, meaning individual particles actually don't really encounter collisions. Or also we can study supernova remnants as still one of the best candidates for cosmic ray accelerations in our galaxies. Something that may occur as sort of a bonus, if you look at a remnant of an exploded massive star, is that you see a little object here in the middle. And in this case, this is really just a white spot. What this is a neutron star. So basically the leftover of the stellar core that has collapsed. And the reason we see it in this object is simply that it is a very, very hot ball of matter that simply glows through black body radiation. But not all neutron stars are so tame, so to speak, because they're so-called pulsars, basically rapidly spinning neutron stars, which due to their high magnetic field accelerate particles outwards. And this rotating magnetic field leads to pulsating emission, which led to them having this name of pulsars given to them. We can also call them rotation powered pulsars to indicate that their emission is powered by their rotational energy and not, for instance, by accretion. But what is very interesting is the particles accelerated on this neutron star, they are not lost. They travel away from this neutron star, they diffuse outwards, and they produce these beautiful structures called pulsar wind nebulae. So basically, what we see in this image here on the right is a very famous pulsar wind nebula, the Crab pulsar wind nebula. And we see here synchrotron emission. So again, these energetic particles traveling outwards. And I think in this little animation, if my internet is good enough, you can see how the particles are really diffusing away from the source. And in X-rays, or also in the radio band, we can see their synchrotron emission. So basically, these particles interacting with magnetic fields. These can also be seen in gamma rays through a process called inverse Compton emission. So basically, Compton upscattering of ambient radiation fields that leads to very, very high energy gamma ray emission. And if we look at such pulsar wind nebulae in X-rays, we can learn, for instance, about the spectrum or the distribution of the relativistic electrons of the cosmic rays in the system. But we can also try to understand the magnetic field strength and even morphology throughout the system. So this sort of broadly introduces some of the objects that I want to talk about later, but I also want to introduce to you the mission whose results I'm presenting, and that is the eROSITA X-ray telescope. Now, this is what we call a soft X-ray telescope, simply to indicate that we are detecting photons there of around a few kilo electron volt energies. And it is a space mission that was launched on a German-Russian satellite called Spectrum Röntgen Gamma, SRG. And it was launched in 2019 with the original goal of carrying out a new and very deep X-ray all-sky survey. So basically, it continuously scans the entire sky to produce a map of the whole sky, which would be many, many times deeper than the previous all-sky survey by eROSAT. Now, unfortunately, since this is a German-Russian mission, the changes in the political situation have forced the German eROSITA team to shut down the mission once Russia invaded Ukraine, so that only around 2.2 years of this full 4-year all-sky survey were achieved. But I hope to convince you that we actually can do quite a lot with the data that were gathered since then. Now, just a few informations about this telescope. You see here on the right an image of the eROSITA telescope from as it was still in the lab. And what you will notice is that it sort of looks like a honeycomb structure, as it actually consists not of a single X-ray telescope, but of 7 identical so-called telescope modules. And each of these telescope modules is basically an independent X-ray telescope, which has a CCD X-ray detector and a typical field of view size of around 1 degree. And simply by adding all the data together, we get a much, much larger collecting area. And since eROSITA was designed as a survey mission, the defining characteristic was its ability to carry out surveys efficiently. This means it has a large field of view and a large effective area, so a large sensitivity if we combine all the telescopes. And this curve here on the right shows something that we call the grasp. So basically the product of the effective area and the field of view size of the telescope, which basically shows us how efficiently large areas can be mapped in a certain amount of time. And you see this red curve, which corresponds to eROSITA, significantly outperforms all other X-ray telescopes, past or present, showing that eROSITA was really built to be a survey machine. Now, while I think this one may be well known to X-ray astronomers, what is a little bit less well known is that we also have an improvement in spectral resolution. Now, these X-ray CCD detectors, they allow us to roughly reconstruct the energies of the incoming photons simply by more or less counting the number of electrons released when a photon hits the detector. And here we have a comparison of spectrum of the same source, supernova 1987A, one taken with eROSITA, which are these black scatter points more or less, and one taken by Eximum Newton, which is another very popular X-ray telescope. And you can clearly see a lot more narrow emission lines, or narrow-ish emission line in the eROSITA spectrum compared to this much more blurry looking Eximum Newton spectrum. So actually, eROSITA actually provides an important step towards reconstructing also spectral information from astrophysical X-ray sources. Now, I'm sure you've all seen this beautiful image which corresponds to the complete data taken in the first eROSITA all-sky scan. So basically the first 6 months of eROSITA survey operations. And there's tons of things to talk about in this image. I would just like to point out that what we see here is basically the whole sky projected on this sort of elliptical area. And the galactic plane goes through the center of this image from left to right. And you can see this through a sort of blue strip of emission, blue meaning the hardest energies, because in the galactic plane, we have lots of foreground absorption, meaning we don't get a lot of soft photons reaching us there. Something to keep in mind, that was the case even before the political situation worsened, was that the sky is sort of strictly split between the German and the Russian analysis consortia, with the German part, which I'm a part of, having access to the western part of the galaxy. That means almost all results I will be showing are exclusively based on this western part of the galaxy. And actually, since I think around 1.5 years ago, you can also play around with eROSITA all-sky data, as this first 6-month scan has been publicly released. And I'm showing here just 2 reconstructed images. Now, these circles basically represent not the full sky, but just the half of the sky anymore. And here was tried to separate the diffuse X-ray emission from the point-like X-ray emission. And I just wanted to show this to illustrate sort of 2 rough quantities that we can characterize this survey with. One is we have around 900,000 newly detected X-ray point sources, which is around as much as were known before eROSITA in total. And the other one is we have around 100 million X-ray photons that come from diffuse emission. That shows you that also if you want to study diffuse sources across the whole sky, there's plenty of statistics to work with, simply because the whole sky is such a huge area. Now, I think this is enough of introduction of the instrument itself. Now, I would like to start by showing you a few of the more or less unexpected results by eROSITA, not just limited to supernova remnants, as you will see, but some of the most important, let's say, galactic sources that were studied or discovered. And the first one, I think, jumps right at you if you stare at this image for long enough. And what I'm talking about is you see this very bright northern sort of bubble structure, which is nicely more or less symmetrical regarding the galactic center. And if you look closely and you focus on this green band of emission, you will see that there's also a similar but fainter bubble extending to the south. I've tried to indicate it here with a dashed line. And these structures have been discovered basically as soon as this all-sky map was created, and they have been nicknamed the eROSITA bubbles. Now, the reason this name eROSITA bubbles was so intuitive is because they were actually not the first bubbles discovered on the sky. There are also the well-known Fermi bubbles. So shown in this image here on the right, we have gamma ray emission from the sky from the Fermi LUT collaboration compared with the image of these eROSITA bubbles. And you see in red, there's this similar double-lobed bubble structure around the galactic center in gamma rays. That means we have thermal X-ray emission from these eROSITA bubbles, which seem to sort of surround non-thermal gamma ray emission, so probably some cosmic rays there. And it's actually very challenging to try to understand how these bubbles look like in 3 dimensions, how they would look like from the outside, because we're basically inside the galaxy, and it's hard to deproject this whole phenomenon. But this is a sketch that was produced in the Discovery paper, in which basically you have these sort of more spherical X-ray emitting bubbles, the eROSITA bubbles, surrounding these more oval-shaped Fermi bubbles. And the idea is that this, of course, makes them structures that are as large as our galaxy as a whole, so really galactic scale structures. And these might have originated from several candidate scenarios. One of the candidate scenarios would be that there could have been lots of star formation activity close to the galactic center in the past, which would have led to sort of a large-scale wind blowing material out of the galaxy. Another one would be that our Milky Way black hole was a lot more active in the past and has sort of launched an energetic jet outward. And we're currently working on a new interpretation of this geometry. So stay tuned for a few more months, which is when we should have this new work out. But if we look at this image of the whole sky and we focus on a bit smaller regions, the keen eye may notice there are a few individual specks of emission. And one of these little blobs that we see is this one that I'm indicating here with the square, which has been called the Huygens supernova remnant. Now, the reason that we know this is a supernova remnant is because it shows this very diffuse, sort of very soft X-ray emission from hot plasma, but also because it has a defined radio shell. So basically you have non-thermal electrons surrounding diffuse hot thermal plasma. And this was interesting because it was A, relatively large on the sky, and B, it was at a very high galactic latitude. So we did not really expect to find supernova remnants at these high latitudes. And our preferred interpretation is for this very, very soft object is that is a relatively old, so more than around 10,000 years, and relatively nearby supernova remnant. That means that its apparent height above the galaxy does not correspond to such a crazy three-dimensional height from the galactic plane. And interestingly, in the last few years, there have been a few more discoveries of such supernova remnants outside the galactic plane at large latitudes, not just in X-rays and not just with eROSITA, but it really seems there are more such leftovers of exploded stars far away from the galaxy than we thought. Now, if you look at this image, you may think that this is also a supernova remnant because it clearly shows some very nice circular shell. This is an image that was taken in the first eROSITA all-sky survey. And what is seen here actually has nothing to do with the actual explosion of a star. What is shown here is the region of an X-ray binary, which listens to this phone number, MaxiJ1348. And it turned out that this X-ray binary had undergone an intense X-ray bright outburst around 400 days before this eROSITA image was taken. And what we see as this circular shell is really something like a light echo. So we have a dust layer intervening between us and the source, and the light has sort of had an extended way along the way, getting scattered by this dust layer and producing this perfectly spherical shell. And it turns out by solving this scattering geometry, which is shown here on the right, so basically by measuring A, the time delay between this X-ray image and the original outburst from the source, and B, by measuring the size of this scattering ring, one can very precisely reconstruct the distance to this source, which was found to be around 3.4 kiloparsec, which was not possible with previous measurements. Another outburst, although a much more extreme one, was found completely randomly by eROSITA, and that was a region of a source called YZ reticuli. And what is shown here on the right is basically 3 snapshots by eROSITA as it scanned this source in 4-hour intervals. So basically each 4 hours it scanned this source for like 40 seconds or so. And you see in the early snapshot, there's pretty much nothing. In the late snapshot, there's pretty much nothing. But in the snapshot at the time of interest, there's this insanely bright sort of ring-like looking source. Now this ring is a common feature in X-ray detectors. If you see a very bright source due to an effect called pileup, basically too many photons have hit the central part of the detector so that the detector simply had to discard all the events as they could not be evaluated correctly anymore, which produced a sort of hole structure. And the source that produced this, YZ reticuli, is actually a nova. So basically the explosion of a hydrogen burning layer on top of a white dwarf. And it turns out that it had been predicted that such nova would produce a so-called X-ray fireball. So basically a very short-lived, very hot plasma just after this hydrogen layer has ignited, which would then disappear very rapidly, as you can see, within 4 hours. And this discovery, which was completely unexpected, actually ended up not just in Nature, but it even made it on the Nature cover, as is shown in this very nice animation here on the right. So yeah, this work by Ole König et al. Was really a very unexpected result, but that just shows how having all-sky coverage can, reveal even unexpected sources. Now, this sort of concludes this first tour of, let's say, completely unexpected discoveries. And now I want to show you that we can also learn a lot about sources that did not surprise us at all, that we knew were there simply by having this extremely large area coverage. And I want to do this by talking about something I call Vela and Friends. And if we look at the all-sky map, we're now here in the galactic plane in the region of this bright and extended supernova remnant, which is called Vela. Now, if we zoom in on this region, we get this image here on the right. So you see this sort of yellowish looking structure, which is very extended, around 10 degrees in diameter. And what we see here is actually not just one supernova remnant. In the background, this sort of yellowish looking shell, this is what we call the Vela supernova remnant, which we know is relatively old, a few 10,000 years, and very nearby at around 300 parsec, which explains this very large size. And we know it is a core collapse supernova remnant, so the remnant of a massive star, because here in the center we have a pulsar called the Vela pulsar, which is very bright as a point source and also has a pulsar wind nebula. But on top of this very white shell, you see a few other things. What you see, for example, is this even brighter shell, which we call Puppis A. So this is a completely independent supernova remnant, which we know is A, much younger than Vela, and B, much brighter, simply because it is in a denser environment. And you will note there's also this sort of bluish looking point source close to the center of this remnant, showing that this is, again, a core collapse supernova remnant. This point source is a neutron star. And as it happens, this remnant, Puppis A, was covered in an early eROSITA calibration observation for a longer time. So this provides us a nice opportunity to look at what the data from eROSITA actually look like if you have a lot of statistics. And what we have in eROSITA is, of course, on one hand, we have imaging observation in different energy bands, but we also have spectral information. So if you simply do a histogram of all the detected events and bin them by energy, you get a spectrum such as this one, where you clearly see these broad-ish emission lines from different elements. Now, what we can do is we can divide the spectrum into discrete energy bands, maybe to isolate individual emission lines. And in each of these energy bands, we can look at the image of the remnant. And if we do that, we get this animation that is shown here on the right. So now we're sort of stepping through energy band as we're looking at the supernova remnant. And some changes are rather slow. For instance, you see the northeastern part of the emission is very, very hot. This explains this hard emission, whereas this southern part is highly absorbed, which explains the lack of very soft emission. But what you will also notice is that if you alternate between individual energy bands, some features pop out and disappear again. For instance, if we go to these higher energies and we focus on these clumps that are seen here in the upper part of the supernova remnant, we see there are features that appear and disappear again. And that is simply because our energy band covers a certain emission line and then doesn't cover it anymore. So these regions are rich in emission from a certain element, which indicates there's ejecta produced in the supernova there. Now, of course, this animation is very interesting, but to quantify this more, what we did is spatially resolved spectroscopy. And in practice, what we did here was to simply divide the region of this entire remnant in many, many separate regions. And in each of these regions, we can then extract an X-ray spectrum. Such an X-ray spectrum would look something like this. So basically, you have, again, a number of photons detected per unit energy. And we can then fit this with a model, which includes thermally emitting plasma. And this model will then tell us, for instance, the density, temperature, but also the different elemental abundances inside this plasma. And one crucial aspect here is that in such young supernova remnants, we have something called non-equilibrium ionization. That means the shock wave has interacted with the surrounding medium, but when this happens, the different species, so electrons, ions, protons, actually assume different temperatures due to simple thermodynamics, and they don't immediately equilibrate simply because collisions are so rare. So that means that in such X-ray spectra, we actually see such a signature of non-equilibrium ionization, which affects, for instance, how different emission lines look. And the strength of such non-equilibrium ionization is described by a parameter that we call ionization age. And now this parameter is what is shown here in this upper panel, where these individual sort of polygon-like regions you see simply correspond to these colorful ones we had in the previous image. And what this basically means is the higher this ionization age is, the more collisions it has undergone since it was heated. That means the closer it is to equilibrium. And it turns out we can actually parameterize this simply as a product of the electron density and the time that has passed since shock heating. Now, it turns out we can also estimate the electron density from our spectra simply as it relates to the global normalization. So what we can do here is we can divide out this dependence on electron density and isolate what I call here the shock age. And then we get a map like this. So basically here we have the brighter regions. They have been heated a long time ago, or the plasma there has been heated a long time ago. The darker ones rather recently. So this is really providing us with a history of shock heating in this supernova remnant. And we can see there are some regions which have been heated as recently as around 500 years ago, so only 1/10 of the age of the supernova remnant. And just to show that what this is not just a hallucination, if we link to the actual image, we see these correspond to some filaments which clearly also stand out in their emission pattern, or as is the case of this rectangle on the left-hand edge, this is actually where the shockwave is interacting with a dense molecular cloud. So there's really currently a lot of interaction going on. However, we cannot just do microphysics of shocks. What we can also do is do a sort of a census of the different elements by isolating their elemental abundances as our spectra tell us. And what is shown in these 6 maps are basically each panel corresponds to a different element, and the colors indicate the elemental abundances normalized to the solar abundance. So values of 1 in this map corresponds to the solar abundances, whereas higher values are supersolar. And if we just compare these maps, we will see very quickly there's one region which pops out most clearly in silicon, I think, where we have almost all of the ejecta-rich material. So there we have lots of enrichment with light elements, whereas other regions are relatively poor in that. So it seems to be that there's basically just one X-ray bright clump in the supernova remnant where we see ejecta. Now this is interesting because we can there's another fact about PUPIS A which I have not mentioned, and that is the neutron star in its center is moving rather rapidly towards the lower right with a few hundred kilometers per second, and that is because during the explosion of the supernova it has experienced a kick. So basically it's being recoiled by the heavy ejecta that were expelled in the opposite direction. So theory predicts that you would see the heavy elements in the opposite direction of this kick direction. And if you actually do the geometry here and compare to the centroid of heavy element ejecta such as silicon, you see the directions don't fully match each other. So either there seems to be something, this theoretical prediction is not as precise as we thought, or maybe it has to do simply with a bias of what we see in the X-ray emitting part of the ejecta. Now, zooming back out, going back to this Vela supernova remnant, I want to talk a bit more about what we see in this image. And something that is very interesting, I think, is to change the color scale, sort of from this logarithmic, evenly looking scheme to a linear scheme where we see colors more clearly. And there's lots that pops out in this image. But what I think is most interesting are these blue sort of emitting regions. And one of these is this almost circular shell that we see here. And as it turns out, this is yet another unrelated supernova remnant, which has been nicknamed Vela Junior due to its location. And we have studied this in 2023. It turns out this is really a purely synchrotron emitting supernova remnant. So there's no thermal plasma which we can detect in the supernova remnant. It's really only relativistic particles. The other thing that stands out here is a region called Vela X, which is basically the historical name given to the pulsar wind nebula surrounding this central Vela pulsar. And this is more really, you can see here a very diffuse appearing emission, simply because we really have the electrons slowly moving away from their central source, which produces this very smooth emission gradient. And in any case, I think we can see from these images that the eROSITA data allow us to disentangle thermal and non-thermal emission basically across the whole sky or across very large areas for the first time. And just to show 2 examples of what we can do with this, we can actually repeat the game that I did before and produce such maps of typical elements across the supernova remnant, again with the abundances being shown in solar units. And just glancing at them in detail, you will see oxygen, neon, and magnesium sort of show similar peaks where they have enhanced abundances. So these seem to be clumps of ejecta-rich material, whereas iron does not show these same clumps. And this is actually something that is not surprising because oxygen, neon, and magnesium are so-called light ejecta elements. They're produced, or these are alpha elements, meaning they're basically just an accumulation of alpha nuclei. So you actually expect them to sort of trace each other in a supernova remnant, whereas iron sort of comes from the center of the exploded star, so completely different region. And what we can do here is we can actually try to study the composition of these ejecta in more detail, but by basically looking at each of these treating each of these regions here as one data point and measuring the relative composition of these of the material there. So what we did was to construct basically neon to oxygen and magnesium to oxygen mass ratios. And if we simply plot the distribution of all these regions that we just saw in the image, you will see that they end up in this right region here. And for comparison with the X, I'm showing you the solar composition. So you see, you have really an incredibly strong neon enrichment compared to the solar composition, for reasons that are not entirely clear. And not only is this strongly supersolar, if we look at popular models of nucleosynthesis in such a supernova, so if we look at models that tell us how much neon, how much oxygen is produced in an exploding star, you get all these markers here, which basically show you different stellar masses, but none of these really seem to overlap with the observed composition of the ejecta. So again, either something is wrong in the evolution in these nucleosynthesis models, perhaps in the progenitor evolution, or it's really some bias that we get in our X-ray analysis of the ejecta. Now, what I also want to talk about more is this central pulsar wind nebula that we saw, that I told you is called Vela X. And actually, before eROSITA, we knew quite a bit about this pulsar wind nebula, but only on very small scales. So now this image here is on the scale of a few arc minutes, and it shows you sort of the time evolution of the non-thermal emission in this area. And you see this beautiful structure with a central torus and this sort of time variable jet. But on much larger scales, there was not so much known. Actually, the best available data covering the whole region was by ROSAT, so by the previous all-sky survey. And this image shows you basically what we knew beforehand. And here in the center, we have the pulsar, and then we have this sort of filamentary emission extending towards the south, which has been called the cocoon. But apart from this area of emission, it was not really clear where the pulsar wind nebula stops, for instance. But now what we can do with eROSITA is we can use the spectral fitting that we did before and measure the non-thermal flux across the region of the whole remnant. So this is really an image which is around 10 degrees across. And in this image now, the brightness of the individual regions indicates how much non-thermal emission there's there. And once again, we recognize these two structures that I mentioned before. One, this shell-like supernova remnant, Vela Junior, and then two, this extremely extended pulsar wind nebula, reaching around 3 degrees from the central pulsar. So this is really much bigger than what we knew before. And in order to understand what we are seeing there, we need to quickly look at this cartoon, which sort of shows us what we think happens when such a pulsar wind nebula evolves inside a supernova remnant. And basically, there are 3 stages here. In the first one, basically, the supernova remnant expands peacefully, and the pulsar wind nebula is sort of undisturbed in the center. But the second stage happens as soon as this reverse shock that I mentioned before reaches the pulsar wind nebula and sort of crushes it. And this crushing leads to a fragmentation of the central pulsar wind nebula and also to the diffusing away of electrons. So my interpretation is that this jet-like structure, this cocoon that we saw before, is sort of this relic pulsar wind nebula, whereas the extended emission is really from electrons diffusing away until they sort of lose their energy. And we can actually also show this more quantitatively by making, out of our map here, by making a radial emission profile. So basically we do a coordinate transformation, starting here from the center, and measuring for each region how far it is away from the pulsar. And then we get a radial emission profile like this one, where again, each marker corresponds to one region. And this black line here shows you the broad average emission. And there's actually a second black line here, a dashed one. And this actually shows you the expectation for such a model of particles diffusing away. And these match very well. And we can parameterize this with a typical diffusion length of around 14 parsecs. So this is what we can think of as the scale of the emission. And this is determined only by the diffusion, so the speed of particle transport, and by the lifetime of the particles. So for instance, determined by the magnetic field. So from that, we can really learn about, what are the properties, how is the transport of these particles governed in such a pulsar wind nebula. Now, something that is a little bit more confusing is if we compare this X-ray emission, which is shown here in the center, to multi-wavelength emission from this pulsar wind nebula. On the left is shown the radio regime, on the right there's shown the gamma ray regime, and all of these are known to come from relativistic electrons. But if you compare these morphologies, you see, especially in the part north of the pulsar, there only seems to be X-ray emission, but there's no radio emission, also no gamma ray emission. So there's really some discrepancy that could be either, again, due to instrumental biases, especially in the gamma ray regime, or, for instance, also due to magnetic field variations. Now, this ends this sort of extensive chapter on one of my favorite objects, the Vela supernova remnants. And now I just quickly wanted to show you what we can learn on sort of populations of different type of sources in our galaxy. And one of these goes back right to this sketch of evolution of a pulsar nebula, because I had previously omitted this third stage, which we call the halo stage, in which the pulsar is basically moving through the free interstellar medium, and you just have electrons moving away from these. And we know that this stage occurs because there have been observations of such so-called pulsar halos surrounding nearby pulsars, for instance, the Geminga pulsar, which have been observed by this gamma ray observatory HAWK. And as I told you before, when we have such TeV particles, we would also expect synchrotron emission simply because there's an ambient magnetic field everywhere in our galaxy. Now, my colleague Aliona Hochryakova has set out to measure this synchrotron emission with the eROSITA data, basically looking at a few of such nearby middle-aged pulsars, and by performing basically something like photometry, masking all the known sources and constraining the observed emission in these areas. And what she found was actually no detectable X-ray emission. And this is not just a negative result, this is actually a very constraining upper limit, because this tells us the magnetic field in the regions of these halos has to be quite low as almost 1 microgauss for this Geminga pulsar, which is quite low also compared to what we typically think magnetic field in our galaxy should be. Now, going back to this all-sky image one more time, we can also study the population of supernova remnants in galaxies, because we have a very large area available. We could do this in our own galaxy, but due to the strong absorption in the galactic plane, this would be very biased. But a place where we can do such studies in a much less biased way is this little blob down here, Large Magellanic Cloud, our neighboring galaxy. And the reason this is interesting is because the LMC, the Large Magellanic Cloud, is a very nearby satellite of the Milky Way. So we can very nicely resolve structures. It is very face-on and has a low foreground absorption, meaning we can also see soft emission. And what is particularly relevant for eROSITA is its location on the sky happens to be close to the survey pole, so the point that keeps getting scanned over by the eROSITA mission, which means it actually obtained a very, very deep exposure. And this beautiful image here on the right is actually the cumulative available eROSITA data of the Large Magellanic Cloud. And so what my colleague Federico Zangrandi did was to try to do an unbiased study of supernova remnants in the Large Magellanic Cloud, sort of looking at previously identified candidates and also identifying new candidates. And this image here on the right shows you in white all the new identified supernova remnants or candidates, and in green all the previously known ones on top of the galaxy. And in total, there's almost 100 systems known in the LMC now. And there are a few things that are interesting here. One, there are these two sources on the lower left edge of the image. Actually, they would be outside of the image if we didn't crop the image appropriately to include them. And these were at first just known to be candidates, but due to follow-up observations led by my supervisor, Manami Sasaki, it was actually shown that these are also supernova remnants, and their distance is compatible with the distance of the LMC. That means the progenitors stars of these supernova remnants must somehow have been ejected from the area where all the stars are in the LMC, perhaps due to some tidal interactions. But these outskirt objects are not the only weird thing about the LMC. Another thing that emerges is if we try to do a luminosity function. So we basically measure how many supernova remnants are there with a certain luminosity or above a certain luminosity. And we compare this luminosity function with the ones that were found in other galaxies. And what is shown here in this graph on the right is this luminosity function in red for the LMC and the other colors for other galaxies. And I think you immediately see at the highest luminosities, the LMC really stands out. So overall, it has to be described with a flatter slope. And now one can wonder, okay, is this just some observational bias? Or is this really an effect that is unique to the LMC, perhaps because it has such active star formation? Maybe there's something different about the densities in which stars typically explode, for instance. But that is really something interesting that we're currently investigating. And finally, I just wanted to give you a quick glimpse at the LMC and what happens if we go ahead and exclude everything that looks like a well-defined compact source in this image. So every X-ray binary, every supernova remnant, and so on, and simply look at what remains. This image now shows my best attempt to do this, and I hope you will agree with me that there's actually a lot of emission remaining. You have a lot of diffuse X-ray emission in this galaxy. So what I think we see here is really hot X-ray emitting gas that is not caused by individual supernova remnants anymore, but there's actually a hot phase of the interstellar medium. And we actually know that such a hot interstellar medium phase should be predicted because this goes back to the original pictures of the interstellar medium that predicted a 3-phase, so cold, a warm, and a hot one. And this hot phase really has temperatures upwards of 1,000,000 Kelvin and extremely low densities, down to maybe 10 to the minus 3 particles per cubic centimeter. And what is interesting is the only way to get the plasma to such high temperatures is through stellar feedback, which is basically a fancy word for the energy input from supernovae or stellar winds. But that also means that the distribution and the brightness of this gas traces the stellar feedback. And as my final plot, I just wanted to show you this multi-wavelength comparison of our knowledge of the interstellar medium in the LMC. So basically what you have here is you go from the top left to the bottom right to higher and higher energies, and you see what kind of diffuse emission you see in this galaxy. So top left, you have diffuse emission from cosmic rays. And then the next two channels basically show you cold gas and dust. And these reveal really some broad filamentary structures, but also some clear cavities, which are sort of empty of cold gas. And this goes down all the way into the near infrared. So in this lower left image, you start seeing also where the stars are. And you see the stars are mostly concentrated in this cyan emission band, and they sort of extend diagonally in the so-called bar, the LMC. So the stars are really in a different location or concentrated in a different location from where the gas is. And the central panel shows you what I think of as the warm phase of the interstellar medium. So for instance, H2 regions, planetary nebulae, also some supernova remnants in different optical emission lines. And I just wanted to show you that now with eROSITA, we can complete this picture and show you the hot phase of the interstellar medium. So really gas that is a few million degrees hot. And what is noteworthy, I think, is that it's it seems to be very, very volume filling. So there's almost no gaps in this emission. And if there are, they may be explained by absorption, for instance. So it really seems like this hot gas permeates the majority of this galaxy. Now, with this little glimpse to the very large scale emission, I would like to get to the end. I'll just quickly summarize. I hope to have shown you a little bit of what we can do about the stellar graveyard. So basically supernova remnants, pulsars, pulsar wind nebulae with eROSITA all-sky survey data. And this sort of rests on 3 pillars. One, the fact that the all-sky survey allows us to make discoveries even where we didn't expect anything, even where we didn't expect there to be anything. For instance, new bubbles, such as this Huinga supernova remnant or the eROSITA bubbles, and also sources that happen to be an outburst where nobody else would have looked. But also we were able to study well-known sources simply by using the fact that eROSITA covers such large areas of the sky, and we can study those systematically and with very uniform coverage. And this allowed us, for instance, to map where the ejecta are distributed in these different supernovae, Vela and Puppis A, and also allowed us to constrain the very, very large scale synchrotron emission from the Vela X pulsar wind nebula. And finally, we can now also, with this all-sky coverage, we can start doing population studies. So really not just look at single objects, but really try to pick a sample of objects of a certain type and see how their properties are in a statistical way. And finally, I would just like to emphasize the eROSITA first all-sky survey has been public for like 1.5 years. So there's really nothing stopping you from also playing around with the data a little bit and seeing what there's in there. And thanks a lot. I hope we can discuss some of this.
Thank you very much, Martin. It's always a very nice pleasure to hear supernova remnant talks because of the nice images and so on. And this one was full of them. Thanks a lot. So are there any questions? Let me see if there are any. There's one in the chat, if you don't mind. Maybe I can just read quickly. Suba says, you mentioned that finding a large remnant like Huinga at such high galactic latitudes was unexpected. Do you think this discovery implies a significant hidden population of old, faint remnants in the galactic halo that we may have been missing? And how this might estimates on supernova 8?
Yeah, I mean, I've been trying to sort of indicate this hidden population, and there really seems to be more than one remnant at such high latitudes. However, of course, as it is with such diffuse structures, we never fully sure about the distance. So just because something is high up, it could also be rather nearby and then just a few hundred parsec above the plane and not a few kiloparsec. So I would still be a bit unsure about how many remnants are really out there in the galactic halo. And I would also think that this is probably still these are interesting cases, but probably these are not the main occurrences of supernova remnants. So I would still think that many of or most of the galactic supernovae are more or less close-ish to the galactic plane. And actually, I think, unfortunately, eROSITA is probably not the best for looking to the other side of the galaxy, simply because we have so much absorption. But I think if we look at MeerKAT or ASCAP, so radio data, there's so many shells that they see that should probably also vastly increase the number of known supernova remnants in our galaxy.
Yeah, thanks. I was going to ask in a similar way. I mean, in that aspect, optical observations would have been helping in these kind of discoveries, right? I don't know, some of the very wide field remnants may be hard to detect in optical, but
yeah, this is a very good point also. Actually, this Hoinga supernova remnant that I showed was almost simultaneously discovered also in the optical, I think through H-alpha filaments. I think it was by Robert Faison et al. And I think they published their discovery just a few months after our X-ray discovery was published. So these appear in the optical, and I think also other of these examples appear in the optical. The problem is just, I think, to my knowledge, there is no homogeneous all-sky survey at the, for instance, H-alpha or O3 that would reach the resolution that you need for these filaments. So you mostly rely on people looking in the right direction and finding it.
Yeah, you're right. Are there any other questions? No more, thank you. All right then, Martin, thank you very much one more time for your time for this very nice talk. Well, see you next time then. Thanks a lot.
You're welcome.
Bye.
See you.
Thank you.